So now we have a presentation coming from the east of Paris, Université Paris-Est, and with Vittorio Sansalone, who made his in Rome.
Thank you, Samuel. Thank you, Samuel. Thank you, Francesco. And I will be talking about bone biomechanics. And my talk, with respect to the one we had this morning, will be focused on a more fundamental question. What's the nature of the actions driving bone remodeling? So I will spend some word about biophysics of bone before going through the model. But first of all, let me acknowledge the work with some people coming from my same lab from Rome, which the guys in red are the most involved in this research, but I had useful discussions with other people from elsewhere as well. So, first of all, I want to thank the speaker of this morning, since he gave a very nice introduction that will make me spend, to be short, in giving you the goal, the motivation of this work. It was said, everybody is concerned, and osteoporosis and bone diseases are a very important issue. It is estimated that fragility fractures related to bone diseases is the second most important social problem in healthcare after dementia. And we have already heard about the differences between a normal bone and osteoporotic bone, as well as the fact that osteoporosis, which is a kind of genetic disease, is not the only action which would justify this bone structure, since after a long bed rest, or even for astronauts coming from a microgravity environment for several months, their bone have similar structures to the ones of osteoporotic people. Why? Because bone is able to optimize, to adapt itself to its prevailing mechanical, but I will be focused also on biomechanical environment. So my talk, there are two main questions, and I will focus on which are relevant in bone biomechanics, which are mostly concerned with these two parts, these two ways, which I try to depict in this picture. Bone remodeling is something which is important at the organ scale for physicians. They want to understand how to improve bone strength. But in order to do that, they have to understand that we want to contribute to this kind of, to that, to understand how biomechanical stimuli can be transferred from the organ to the cell scale, where the bone cells, which are the real actors of bone remodeling, can be activated, can act in order to remodel the nanostructure, the microstructure of bone up to the organ scale, when we can observe such a beautiful and very well organized structure. So these two terms, mechanomics and materiomics, refer more or less, are two very new terms. This was introduced in 2006 in the World Congress of Biomechanics, and this is even younger. And they refer to these two ways, which are of course concerned with each other. But for today, I will be only speaking about the very last part. So bone remodeling at organ scale. So at that scale, remodeling can be perceived as a change of shape, but not only that. Actually, if you look inside the organs, we can see that there are several kinds of microstructures. There is a kind of dense outer shell, what is called cortical bone, with a spongy material inside, which is the trabecular bone. And these structures are not always the same according to the anatomic site. For instance, in the sternum or in the femur. In the femoral head, the microstructure of the trabecular tissue is different. So why? Because the mechanical forces that these two bones are supposed to support are not the same. So in there we need less bone matter than in here. Moreover, you can see that in the sternum there is no specific pattern which can be perceived, whereas here there are specific directions, so isotropy versus anisotropy. This is very interesting. Also, the cortical tissue has a very specific microstructure organized in this way. There are some cylindrical units called osteons, which also are have a major role in supporting the mechanical forces applied to bone. But maybe the most known picture is this one when talking about bone remodeling. This is a picture coming from the 19th century where Wolff's, which gave the Wolff's law is maybe the most known principle for when talking about bone remodeling, observed that the structure of the trabecular bones is very similar to what would be the best structure in civil engineering, in a civil engineering structure. And starting from that way, a lot of people have worked about the criteria which would drive bone to that specific microstructure. That criteria have to be to account not only for mechanics but also for chemistry, since in genetic and medical treatment can affect bone structure. Mechanics, of course. This is a picture of a rat tail when it was solicited to a mechanical force or not, and also electrical stimuli. We know now that electrostimulated bone can increase the mass, the bone mass, when this was a turkey, not a human. So the nature of the stimuli driving bone remodeling is manifold. And what we try to do is to develop a model and to understand what's the nature of the very basic mechanism driving bone remodeling, accounting for all these types of phenomena. So, looking explicitly at the macroscopic scale, I will try to explain how we could explain the different bone microstructures that we can observe. In this case, look at these green spots, since they will play more or less the central role in my talk. The green spots hint at the elastic ellipsoid. So, more or less, this is a small green spot. That means not little bone matter with an isotropic structure. In here we will have more bone matter. In there we will have more bone matter and anisotropy. So my talk will deal only with something like that. How to move from one picture to the other one. And since this is still maybe too difficult, I will focus only on that in the latter case, but I will be speaking about in a few minutes. Just to give you the framework, this morning Professor Del Piero has spoken about the framework that I will use to develop my work. This was the counterpart of what we've been talking about, and I'm looking forward for tomorrow's introductory lecture, which will also focus on generalized continua for biomechanics. So, in my case, I will move from the framework of Germain and Kapritz. So, I will try to develop the kinematical, balance, and constitutive structure of the theory. So, what about kinematics and what about remodeling in this framework? Besides the visible placement, remodeling will be described as the evolution of the microstructure. And as I told you, I will make a very simplifying hypothesis, not any kind of evolution, just rotary remodeling. That means that the bone matter is always the same, and what I'm looking at is just the rotation of the elasticity axis. Of course, it makes sense if the material is not isotropic. So there is anisotropy, basically. Okay, this is the kinematics. What about balance? I will use the extended virtual power principle to develop the balance structure of the theory. So in red, more or less, I try to put in red whatever related to remodeling, just to keep things clear. In black, whatever is classical. So besides the classical Cauchy stress or Piola stress in this case, there are additional actions, outer and inner actions, related to remodeling. What are these actions? These actions are the mechanical feedback of whatever mechanical but also biochemical stimuli triggering bone remodeling. The big challenge is modeling these actions. So what is the effect of the biochemical environment on the remodeling? In which way power is expanded? Somehow the virtual power principle is my gauge. If there is bone remodeling, there is some power expanded. Eventually I get the balance equations, the standard balance equations in black, and the remodeling related balance equations in red. I said red, in black and in red. This is a zero order balance equation, so there is no boundary conditions in this case, since this equation is just saying that the outer remodeling stimuli have to be balanced with the inner bone remodeling stimuli. Let's go further to the constitutive theory. This is the critical point. To make things easier, I introduce a free energy density, which is a quadratic measure of the small strain, but the elasticity tensor is not constant in time. It can evolve. Since I'm talking about bone rotary remodeling, the only way the elasticity tensor can change is just rotating. Rotating with respect to the prototypal version, the initial, if you want, elasticity tensor, through a tensor, an orthogonal tensor R. I add a proper statement of the dissipation inequality, where there are the Piola stress and the remodeling actions, and requiring that this term is greater than the time rate of the free energy, I can end up with some calculation. I can end up with the constitutive law for the stress and from the remodeling actions. In the remodeling actions appear this term, SE, which is twice, I forgot a 2, twice the skew part of the product, SE. This is a very important point, plus or minus, according to the definition, a dissipative contribution. This is a very important point, I was saying, skew part of SE. Why is this? Okay, so let's put everything together, balance, constitutive theory, and let's look at the remodeling law. In this case, it looks this way. And what's inside? In here, the dissipation related to remodeling is equal to this term, twice the product SE, plus the outer contribution that I can put on my system in order to trigger remodeling. Okay, let's switch it off. Let's switch it off, since we are not able to model it properly, and look only at stress-driven rotary remodeling. Moreover, let's use just a linear dissipation. Let's say dissipation is linear, okay, maybe not. The evolution equation that I will end up with for remodeling looks this way. So, as long as this term is not zero, there is remodeling. There will not be any remodeling anymore when this term will be zero. But what does it mean? That means that S and E commute. So somehow there is a result which was unexpected and which was not plugged at all within the model, that the remodeling equilibrium is attained when the eigenspace of the stress and of the strain tensor are parallel. This is exactly what everybody say Cohen and Frost and whatever people, remodeling equilibrium is attained when stress and strain are parallel. I didn't put anywhere this information in the models, and it appeared naturally. It was surprising. So, just to fix some ideas, I will show you some results in 2D, where the rotation is parameterized by a scalar. In this case, I will use data for orthotropic elasticity, and what I will look at is the evolution of this material element, something like that, when applying a one-dimensional, 1D traction in one direction. So it is possible to obtain an explicit form for the evolution law, which becomes a scalar equation in this case. And here is the result. So this term omega is the right-hand side of that equation. So this is, how to say, this is the remodeling stimulus. It is possible to see that there is the zeros of this plot corresponds to the remodeling equilibrium points. It is a p periodic function, so in 0p there are 4 points for that set of data, and some of them are stable, some are not. Green spots are stable, red spots are not, are unstable points. That means that if we look now at the time evolution of what's going on at that material element, look at the blue ellipse, the blue spot represents the strain, the stress direction, the stress ellipsoid, which is constant, 1D traction. And the red one represents the strain ellipsoid, which evolves in time according to the evolution of the elastic tensor. In here, the stress is constant. So what is going on in time is that the strain aligns with stress, whatever the initial condition we start from. So somehow the remodeling equilibrium is a very stable finite state for that model. The problem is that this is the remodeling equilibrium state. So even when moving very close from zero, so the strain and stress where the elasticity axis alpha are almost aligned with the stress direction, the zero, since the 0 point is unstable, the system moves apart from that, which is somehow strange. Okay, I will try to explain to that first. There was a movie. Okay. So, since I thought that the movie wouldn't work, what's going on is that, so you can see here the eigenspace of the strain tensor evolving in time. So the strain directions are the axis of the ellipse, and the size, the length of the axis are the eigenvalues. So you can see that the eigenspace of the strain tensor evolves in time and eventually aligns with the horizontal direction, which is the direction of the applied forces. So why is this result, as I told you, the fact that the stable equilibrium is attained at an angle which is 0.8, it was surprising as well. So I tried to go a little bit further, deep inside the equations, and try to develop an explicit solution for that point. So the idea that was to work on the eigenspace of the elasticity tensor. So first of all, it is possible to obtain an explicit formula for all of that, and what I've done is to project all the quantities, strain and stress, on the eigenspace of the elasticity tensor, which changes in time. Since the elasticity axis changes, so the eigenspace of the elasticity tensor changes as well. Well, it is possible to see that this term, which which is the remodeling stimulus, admits, for the case I'm studying, 4 points. It is 0 in 2 cases. Either when sigma 1, this term, so the projection of the stress tensor on the first eigenspace, this is the first eigenvector of the elasticity tensor, so this is shear and this is axial. So either no shear or something that a strange relation between the other projections. The fact is that when we look at this second case, actually we end up with this formula, and in this case the first condition, no shear, is always an equilibrium, a remodeling equilibrium point. The second condition admits real solutions only in some special cases. It turns out that actually there may be 2 or 4 solutions, and the stability of those points depends on the elastic coefficients that I put in the elastic tensor. That means that the 0 point might be unstable or stable according to the specific value of the elastic coefficients, and more or less it depends. In these 3 plots correspond at 3 different values of this term of the elasticity tensor. So somehow when this shear related term increases, 0 becomes a stable point. When it is small, 0 is not. So there is the how to say, interplay between the actual elastic coefficients, which justifies the final equilibrium state of the material. So I think I'm in time, so I just spend a few words to answer the initial question. Is it an energy, is it a constitutive matter? Bon, remodeling, is it a constitutive matter? Partially. Since it seems that there is something more, something which is related to balance, which comes before the constitutive theory. The existence of a remodeling equilibrium state comes before the introduction of any specific constitutive assumption, but very basic ones. But of course the way we get to that specific, this one or another one, equilibrium point, that is a constitutive matter. So the specific constitutive prescription can drive the system to one or another equilibrium point. And on top of that, in this case, I switched off whatever related to biochemistry. The outer stimulus to remodeling is set to 0. So, should it be there, the scenario would be even more complex, and it would be the interplay between mechanics, this condition which is related only to mechanics, and biochemistry, which would lead the system to a specific equilibrium point which may even not exist anymore in that case. Okay, thank you for your attention.
I did not completely get your model. Is it a kind of evolution equation for the rotations? And then is it altogether a viscoelastic model?
Both of them. It's an evolution model which comes from a dissipative, a viscous dissipation, a linear viscous dissipation. Okay.
What about the choice of the remodeling element? I'm worried about it because the ball is highly homogeneous in macro scale. And then how does that influence the model of T0 or T?
You're completely right. The fact that the material, more or less, this is the material element that I have in mind, 0.5 millimeter, something like that. But there is no deep analysis on that, since this model and the elastic coefficients that I used were taken for cortical bone. But this kind of remodeling is more meaningful for trabecular bone. In trabecular bone, the RVE is, we cannot define the RVE, so this is a point which needs a lot of work to be done.
Due to the application of load, although the degree of anisotropy changes, are you planning to include this in your model waveform?
Yeah, actually I've done independently. I let the elastic coefficients, by the magnitude of the elastic coefficients, change in time, and also in that I didn't do both at once. I did that separately. What's going on is that when I let the magnitude of the elastic coefficients change, they decrease to 0 without any external input. If I don't put any external input, if I put T0 equal to 0, in that case the magnitude decreases to 0. What does it mean? That it seems that it might mean that the mechanical properties decrease naturally in time, in the sense that if I don't put anything in my system, the system deteriorates in time, the elasticity of the system. I didn't do both at once.
Not only the coefficients themselves, but the ratio between the coefficients.
I didn't do that yet. Of course, I had to, since I didn't look at all at the ratio of anisotropy in time. I didn't look at that.
You can explain this product of S&P, the driving force rotation. Where does it come from?
In here, I put this equation exactly for that reason. SE is the derivative of the strain energy with respect to this velocity, which is the rotation velocity.
The next slide. Yes. When you write remodeling law.
When I
When you write remodeling law.
Yeah.
So you have on the right hand side of your equation the product, the commutator basically, and T with the
Note the outer.
Okay. And then you set T naught equal to 0.
Yeah.
This is something you can motivate, of course, but you are choosing.
Sure.
So, why do you say it is natural that remodeling stops when S and P commute? Because this depends also on your choice. If I get some coefficient there, like an interrupter, then I can get different evolution.
No, of course.
If I understand
Of course.
natural at the end.
I said that in this case it is natural when only mechanics is concerned. As far as mechanics is concerned,
Only mechanics is concerned.
Yeah.
Depends on the evolution law you propose.
okay, but whatever out of mechanics is plugged in there. When I put T naught equal to 0, I'm switching off any biochemical stimulus to remodeling.
Of course, but also then, I mean, in plasticity, for example, you have the introduction to choose a criterion, say when plastic deformation begins. And this is because you write your discussion in a certain form. So you can get any type of result by choosing different remodeling laws. The only thing I slightly objective the comment that
Maybe I didn't get your question, but actually I cannot choose any remodeling law. At that stage, the only thing I've chosen is from a constitutive point of view, is this one. I've chosen this free energy density, And this is the only constitutive ingredient I put in the model so far, up to that. So everything else are additional constitutive prescriptions, but they come later.
Last question. If you then your elasticity tensor depend on some rotations, why do you not modify your strain tensor in the same way?
The strain changes according to the elasticity tensor. The strain tensor changes since the strain is computed as C minus 1 sigma S. S is constant, and E, the strain tensor, is.
Modify the strain tensor?
Yes.